Hello, I'm Dr. Rajendra M. Galagali, Associate Professor in the Department of Mechanical Engineering, Chivale Kundra Institute of Technology, Belagavi. Let us discuss about Rankine Vapour Power Cycle, which is in module number 3, Vapour Power Cycles under Applied Thermodynamics. Now, this is the representation of the Rankine Vapour Power Cycle. The schematic representation shows that it has 4 components: turbine, condenser, pump, and a boiler. The Rankine Vapour Power Cycle is represented on the pressure volume diagram and on the temperature entropy diagram. Let us understand the flow of the working substance through these components, completing the cycle. First of all, at state 1, it enters into the turbine. There are 3 possible states which can be considered as state 1. As seen from the PV diagram, the state number 1 is a wet vapor that may enter into the turbine, or it may be at 1 dash, it is dry saturated steam, or it may be at 1 double dash, which is superheated steam. So any one of these conditions can be considered for the working substance, but the most preferred one is 1 double dash, which is superheated steam. That means the steam must always enter into a turbine as superheated steam. That is the most preferred state. Passing through the turbine from 1 to 2, so let us consider this point as 1. 1 to 2 is the expansion that is taking place in the turbine, and there is a work output WT, and that expansion for wet steam is 1 to 2, and if it is dry saturated steam, that expansion is 1 to 2, 1 dash to 2 dash, and if it is the superheated steam, it is from 1 double dash to 2 double dash. As said, the most preferred state is 1 double dash, and the preferred expansion is 1 double dash to 2 double dash. However, in the diagram, it is indicated only for the reference as 1 to 2, which is an expansion process. So it is reversible adiabatic expansion process or the isentropic expansion process. And from 2 to 3, it enters into the condenser at state 2 as a wet vapor, because it's going to expand as a wet vapor as seen from the diagram. That wet vapor enters into the condenser, where the amount of heat rejected to the cooling medium is represented as QR, and it comes out at state 3, which is saturated liquid state. That means wet vapor is completely condensed into liquid at point 3. That enters into the pump, wherein the pressure is imparted, and that pressure is from P2 to P1, which is imparted in the pump. So at condition 4, it enters into the boiler. 3 to 4 is the pressure that is being imported, and also there is a change in the value of the enthalpy. But the state of the working substance, if it is seen, it is at state 3, it is the saturated liquid. At state 4, it is the subcooled liquid state, but at a different pressure or at a higher pressure. Now at state 4, it enters into the boiler and comes out as steam at state 1. The amount of heat added in the boiler is QS. So now the 4 quantities, QS is the amount of heat added in the boiler, WT is the work of expansion from the turbine, QR is the heat rejected in the condenser, and WP is the work input to the pump. So these are the 4 quantities that must be considered in the Rankine cycle. Now the same are represented, QS and QR, on the PV diagram. Now 1, 2, 3, 4, 1 represents the wet steam Rankine cycle. 1 dash, 2 dash, 3, 4 and 1 dash represents dry saturated steam Rankine cycle. 1 double dash, 2 double dash, 3, 4 and 1 double dash represents superheated steam Rankine Vapour Power cycle. Now the same diagram is represented, same cycle is represented on the temperature entropy diagram. 1 within the bell-shaped curve, it indicates that it's a wet steam, and one dash is a dry saturated steam, one double dash is superheated steam. Now from 4 to 1 double dash is a constant pressure line on the TS diagram, which is represented as P1, and that P1 is the boiler pressure. And now 2 double dash to 3, it represents the condenser pressure, which is P2. So that means this Rankine cycle operates between two pressures, P1 and P2. P1 is the boiler pressure and P2 is the condenser pressure. Now here also the three cycles can be distinguished in the same fashion as done in the PV diagram. 1, 2, 3, 4, 1, 1 dash, 2 dash, 3, 4, and 1 dash, 1 double dash, 2 double dash, 3, 4, and 1 double dash. So thus it is Rankine cycle. The work varies: reversible adiabatic expansion in the turbine, which is isentropic expansion, and reversible constant pressure heat rejection in condenser. It's a constant pressure heat rejection, which is at P2, whereas the amount of heat added in the boiler is also at constant pressure P1. And the work input to the pump is a isentropic compression process. Reversible, it is also called as a reversible adiabatic compression process, which is 3 to 4 is a vertical line, 1 to 2 is a vertical line, indicating that these two are the isentropic expansion and compression processes on the TS diagram. Now, in order to find the efficiency of the Rankine cycle, first let us write the expressions for the heat supply, the work of expansion from the turbine, the heat rejected in the condenser, and work input to the pump in terms of the enthalpy change of the working substance. So I consider boiler. Now water enters into the boiler at state 4 and leaves the boiler at state 1. So the difference in the enthalpies, heat gets added in the boiler, that means water is converted to steam. Steam has a higher enthalpy. So that means for boiler, the amount of heat added QS is given as H1 minus HF4. Now condition 4 is written as HF4, that F suffix indicates that it is liquid. And in turbine, there is a work of expansion. The difference in the enthalpies is H1 minus H2. That, 1 to 2, there is an expansion, and 1, the steam has a higher enthalpy, and 2 has a lower enthalpy. This drop in enthalpy is the work output from the turbine. So turbine H1 minus H2. In condenser, heat rejection QR takes place, which is H2 minus HF3, indicating that HF is that state 3 is the liquid state, saturated liquid state. So H2 minus HF3. Then the per pump work is WP, which is HF4 minus HF3. Both are in the liquid state. That means water enters into the pump and water leaves the pump. Both are liquid. So that is why we have written that enthalpy as HF4 minus HF3. So that is how, using this steady flow energy equation as studied in basic thermodynamics, we can write the steady flow energy equation for any of the devices. Because it's an open system, so steady flow energy is applicable for all these devices which are open systems, because mass enters and leaves the system. So all are open systems. For them, the steady flow energy is equation as discussed now. Now, in order to find the efficiency, it is written as the net work output divided by heat supplied, which is WT minus WP divided by heat supplied QS. Now, in terms of the enthalpies, this equation is written as H1 minus H2 for WT minus HF4 minus HF3 for the pump work divided by heat supplied H1 minus HF4. Now, HF4 minus HF3 is the pump work. It is very, very less in comparison with the work of expansion in the turbine, which is H1 minus H2. Hence, this quantity can be neglected in comparison with H1 minus H2. And finally, the expression for the efficiency can be written as H1 minus H2 divided by H1 minus HF4. Since WP is neglected, it's only WT by QS. In terms of enthalpies, it is written. So thus we can find the efficiency of the Rankine vapor power cycle. Now let us discuss about the factors affecting the efficiency of Rankine vapor power cycle. There are three factors which affect the efficiency. First one is boiler pressure. As seen from the diagram, the efficiency of the Rankine cycle increases with the boiler pressure, reaches a maximum value at 166 bar, and further increase in pressure, there is a drop in efficiency. And second one is the degree of superheat. Degree of superheat is the difference between the superheat temperature and the saturation temperature. So that means it talks about the condition of the superheated steam. At what temperature is the superheated steam? So temperature of superheated steam, in other words, is another factor. We can see that as with the increase in the superheat temperature, the efficiency increases, because degree of superheat can be increased by changing the superheated temperature, and saturation temperature remaining the same. So superheat temperature, increase in the superheat temperature increases the efficiency, or degree of superheat, increase in the degree of superheat, different the quantity, the difference between superheat temperature and saturated temperature. With the increase in this quantity, efficiency increases. Third factor that affects the efficiency is condenser pressure. We can see that with lower condenser pressures, the efficiency is more. So lesser the condenser pressure, more is the efficiency. So thus these are the factors which affect the efficiency of Rankine vapor power cycles. There are other ways or means or methods by which the efficiency can also be improved. The first and the foremost method is by regenerative feed heating. Second is by reheating of steam. Third one is by water extraction. And fourth one by using binary vapor. So each one of these will be discussed in detail with the help of the schematic representation and the corresponding property diagrams in the subsequent session. So this is all about Rankine cycle and the factors affecting the Rankine cycle. Thank you.